Welcome back, students. We are basically discussing stereochemical strategies, and today we will be talking about absolute asymmetric synthesis, the fourth guideline which we said falls under the class of stereochemical strategies, and this particular absolute asymmetric synthesis, which is the fourth guideline. If you go to the original pathway, we said 4 guidelines are there, and this is our final guideline. In particular, this part will be trying to focusing on mainly chiral pool approach, as well as if you have a starting material which are achiral, you just need to create a chiral molecule. Now, first we try to focus it more on the chiral pool approach. Now, chiral pool approach is very old approach. The approach says that you need to have some chiral starting material, and why is called pool? Pool means these chiral starting materials are plentifully available in the nature. They are very cheap starting material, and they are basically easily available from the natural resources. So, if I try to analyze the target molecule, we will say that we will try to do a anatomy of the synthesis, means how to execute the entire synthesis. So, you have a target which is essentially a chiral molecule. Now, the target can be first classified to a substructure or a intermediate. Then, as I will try to introduce a new terminology which is named as chiron, then your starting material or source. Now, chirons are basically chiral synthetic intermediate. The intermediate which is having a chirality is called chiron. Now, this particular terminology was first invented by Professor Stephen Hanesian. So, in principle, this chiral pool approach follows 4 different phase or pathway: phase 1, phase 2, phase 3 and phase 4. So, what exactly this individual phase? The first one, we do the analysis that how this target can be constructed through this different. So, this analysis means you have to think about the structural framework of the given target. So, we analyze the certain structural frameworks of the given target and what are the stereocenters you need to construct. Then you do the discovery part. Discovery means you know there are certain chiral pools available in the nature, and you know the absolute stereocenters of those starting materials. So, now try to correlate that how this target structure can be correlated with this starting material. So, this is basically your this discovery part, which will basically analyze. You can close to it substructure, or you can come to a substructure through a proper disconnection, right. And then the phase 3, which basically mainly based on the design, that how do now design this entire pathway, and the phase 4 is now the forward pathway, where you can call about the execution, the entire pathway how you will execute. So, as I said, in nature there are many chiral starting materials or chiral pool materials are available. This can be basically broadly classified into 5 or 6 different categories. You can, let us say, one is amino acids, naturally occurring amino acids. If we are talking about naturally occurring amino acids, there are 20 natural amino acids which are basically naturally occurring amino acids. Now, except glycine, all naturally occurring amino acids are chiral. Glycine is basically having this structure. Other amino acids which are L amino acids are all chiral, and this amino acids are very available in enantiomer form, very cheap starting material. So, this particular stereocenter is fixed. So, if you can use this stereochemical information for your synthesis design, then basically you are using a chiral pool. The amino acid is one of the very good chiral pool. The second is carbohydrates. Carbohydrates are also naturally occurring starting material, and find that there are mainly D carbohydrates in the D form are available in the nature. So, D sugars and L amino acids. Now, out of these carbohydrates you can basically start talking of these molecules like tetrose, you can call about pentose or hexose, all the. Now, say for instance this pentose is basically like a ribose, so D ribose. So, the stereocenters I am now not putting here, but if it is a D ribose you will be or a pentose structure, you basically having this information, you basically having this stereocenter is fixed, this is fixed, this is fixed. So, 3 inbuilt stereocenters you are getting in this molecule. Similarly, hexose, which is basically falls like glucose or mannose, they are having 4 inbuilt stereocenters. Then other chirally occurring starting material is hydroxy acid. Hydroxy acids are also very important starting materials. The first one probably is your lactic acid. Lactic acid, you can get both the enantiomers in the nature. Then the most important one is tartaric acid. Tartaric acid. Now, lactic acid having 1 stereocenter, tartaric acid having 2 stereocenter. Tartaric acid is D or L, which is C2 symmetric, and you also have a mesotartaric acid which is internally compensated or having sigma V. So, you have DL tartaric acid which is having C2 symmetry and meso which is internally compensated having a sigma V. So, this is the hydroxy acid. In addition, you also have other hydroxy acid like let us say mandelic acid is also a naturally occurring hydroxy acid. I do have some other hydroxy acid, I will just try to draw its structure. The another hydroxy acid which is also very well known, its name is malic acid. Now, malic acid normally you can isolate from apple fruit, Pyrus malus, it gives you a rich source of malic acid. So, this 3 hydroxy acid, then you are having compounds like terpenes. Terpenes, mainly monoterpenes are a good source of simple chiral building blocks. Compound like this alpha pinene is a alpha pinene is a monoterpene. Compound like this which is very well known is camphor. These are also you can get one single enantiomeric form in the nature. These are very good starting material. So, this you have amino acids, carbohydrates, hydroxy acid, terpenes, and the list is basically many more, but we will try to figure it out how this chiral pool starting materials can be used in your synthetic pathway or your synthesis design. We will first start with the amino acid and we see the how these amino acids can be synthetically useful for some FGI. Initially I say we will be giving you a amino acid whose structure is this. This compound is basically valine. Now, I say I will be using this starting material and my target structure which I am giving is this epoxide. So, you have to design a pathway by using this chiral pull approach to achieve this target. Now, simple retrosynthetic pathway probably you can think about using this. If you have some leaving group something like this or maybe you can put a leaving group here and put something here O minus, you can immediately close this ring with a inversion of configuration. Now, for these amino acids they behave in a unique way, for a particular reaction. This reaction we will be now discussing. Now, if you are having alpha amino acids, you react with nitrous acid which will basically diazotize the amino acids and will convert this amine group to a diazonium thing. Now, this diazonium compounds having good leaving aptitude and then this OH, this hydroxy OH, it is basically seems to attack this diazonium carbon to give you a very strain intermediate through a SN2 pathway, because SN1 will not be operating here because it is adjacent to a carbonyl group. So, SN2 is very facile here. Now, if you are diazotizing with a HNO2, which is basically means that if you have a NaNO2 and HCl. So, the chloride minus is still there and this chloride minus can act as a nucleophile. Now, this is basically a classic example of a neighboring group participation. A neighboring carboxylic acid group first forms this lactone to give you a strained 3-member lactone. Okay. Then the Cl minus acting as a nucleophile again to give react with this lactone again SN2 fashion, and then basically you will get this compound which is now the original stereochemistry has basically retained. So, we say the retention is basically caused by 2 SN2, means that 2 inversion together, inversion plus inversion give you the retention, and this is very common phenomena for alpha amino acids. Alpha amino acid, if you do a diazotization and then treat with a nucleophile, you can basically end up with this retention of configuration. Now, if you just reduce this carboxylic acid with lithium aluminum hydride, you will get this CH2OH. Now, we are almost close to the synthesis. This primary alcohol you just treat with a base sodium hydride, that will basically give you the alkoxide, and this alkoxide now react in a intramolecular fashion with the backside attack to give you a SN2 and then which now gives you the epoxide as it is. Now, this epoxide is your target molecule, and we have seen that starting from a simple amino acid, the stereochemical information was retained here, and then you get this target molecule as your main product. Similar kind of analysis with these amino acids we will be trying to put in the assignments, and you please basically try to solve it. The next one will be giving away another problem where we will now switch it over to a carbohydrates, switch it over to carbohydrates. Now, this is the carbohydrates, is a 4 member or 4 carbon carbohydrate. This carbohydrate is basically threose. Threose, if you write the linear structure, is basically CH2OH, is a OH here, is a OH and having a CHO. So, this is the threose. Now, I say you start with threose, and I am asking you to make a or synthesize this bis epoxide whose structure is this one. Now, we see the structure, this compound, this bis epoxide having a C2 axis of symmetry. Now, why it is important? If you now analyze the threose structure, threose, if it does not have a OH here, or if its structure is something like, I mean, if it is structure is like this, it is having a perfectly C2 axis of symmetry. So, presence of this OH makes the C2 symmetry is a pseudo C2. Now, how it helps? Now, what you do? You treat this 3OH with sodium borohydride. Sodium borohydride. Now, sodium borohydride basically reduce this aldehyde to give you a open chain compound. Now, this open chain compound, if you now draw its structure, this OH, CH2OH, this bond rotation is free, and right in this particular way, you basically get this compound. This compound is nothing a tetrol, and this is basically the chiral starting material. You come to a substructure or chiron. This is your basically main chiron, chiral intermediate. Now, this compound is also having a perfect C2 symmetry. Now, next, as you can basically visualize that you need to have a okay, the initial after this sodium borohydride reduction, you basically get this compound. Now, what exactly you need to do? This is a tetrol having 2 primary hydroxy and 2 secondary hydroxy. So, I said you react with 2 equivalent of tosyl chloride to get this ditosylate. To get this ditosylate. This is also C2 symmetric, fine. Now, you react with 2 equivalent of sodium hydride. Sodium hydride, what it does? It will be making this corresponding alkoxide in this way, and then this alkoxide will intramolecularly react to give you the structure which was your target molecule. So, stereochemistry of this tetrose was remain intact. Now, you can basically clip this epoxide through either this way or this way, does not matter, because these ends are now homotopic. Anyway, we are not going to discuss it. So, this is your target molecule which can be achieved. So, best thing is you basically try to take this starting material which is 3 O's, we convert it to a tetrol by sodium boride reduction, and you have 2 primary hydroxy, 2 secondary hydroxy. By simple functional group manipulation, the 2 stereocenters of 3 O's was kept intact to give you the target molecule. This is the very powerful way to use the chiral pool starting materials for your synthetic exercises. Next, we will be using little bit complex one, and we will be using a hydroxy acid as our chiral pool. The hydroxy acid which I am basically using is basically tartaric acid, and both the free carboxylic acid was esterified as its ethyl ester. Now, this compound is also having a C2 symmetry, means that this OH and this OH are homotopic, this CO2 to this CO2 are homotopic. The target molecule which was needs to be constructed from here is basically a natural product whose structure is the cyclopentenone based natural product. Its name is plus terrain. Now, if you see a structural analysis for terrain, you will see that this 2 stereochemistry of this target molecule is coming from this tartaric acid. Now, you try to analyze through standard retro how you can convert this terrain and try to analyze how it can be constructed from this starting material. We say that we will be trying to use some reaction. Okay, initially we say okay, you first make sure this free hydroxy group is properly protected. So, best one is to do a acetonite kind of protection, and if this case you will be having some phosphonate kind of thing, you can do a intermolecular Horner-Wadsworth-Emmons reaction or Wittig reaction to make this particular bond. So, now we will be again disconnecting this part here, and now we are saying that if we are having this ketophosphonate this ketophosphonate, say again a C2 symmetrical. We say that first you do a intramolecular Horner-Wadsworth with one of these carbon ion to this carbonyl. Now, no matter which carbonyl reacts, because both these ends are homotopic, both these ends are homotopic due to presence of C2 symmetry. So, this is our chiron. Now, we will try to do the forward synthesis and how this synthesis was done in reality. So, you have a tartaric acid ethyl ester, react with 2,2-DMP or acetone to first protect this tartarate as its acetonite. Okay. So, you will get this acetonite protected diethyl tartarate, fine. Next, I am saying that you react with a methyl phosphonate. Now, methyl phosphonates are commercially available, you can easily make. These hydrogens are extremely acidic, H, H, H. You can basically react with 2 equivalent of n-butyl lithium to generate the corresponding phosphonate anion CH2Li as a nucleophile and react with this ester group of this tartarate. Now, once you react it, you find that this tartarate will now react to give you this ketophosphonate in this way. Now, C2 symmetry remains unchanged, C2, this also C2. Now, this C2 means that this half and this half is homotopic, or this CH2 and this CH2 is homotopic. So, now if we do a intramolecular Horner-Schwarzschild-Emmons reaction by just treating with 1 equivalent of sodium hydride, you generate carbon ion either here or here. Now, this carbon ion can react intramolecularly with this carbonyl compound, and then initially you get your this part is there, your acetonide is here, and you get this double bond here, then your CH2 P double bond O, OET whole twice was there. So, those are the simple FGI, but the visualization was very important. Now, we again draw the cyclopentene compound which we got by intramolecular Horner-Schwarzschild-Emmons reaction, and then you now can complete the synthesis. If you simply react with acetaldehyde followed by H plus treatment to remove this acetonide, you can basically get your target natural product, which is pterine. So, eventually the synthesis was a very nice demonstration of using the two existing stereocenter of this particular tartaric acid, and this stereocenter are basically retained, and in addition we take a demonstration of how C2 symmetric molecule react, as the C2 symmetric molecules are having homotopic ends. These homotopic ends are chemically equivalent. In similar context, we will now take up a carbohydrate derived compound, which we will now analyze the next. A carbohydrate derived compound, which is also a very good chiral pool agent, is this compound. It is commercially available. Its name is D-mannitol. Now, D-mannitol is again a C2 symmetric molecule. Now, from D-mannitol I say that you can prepare both of this epoxide through a divergent pathway. So, this divergent was pretty important. You can basically get RR epoxide or SS epoxide. Now, as time is running out, we will need to be little bit faster. What I am saying, you first take this D-mannitol, if you react D-mannitol with 2 equivalent of acetone, you will initially get the acetonide protected thing, and normally 1,2-diol will react by keeping the 3,4-diol free. So, initially you will get this compounds. Now, next step was very similar or very simple, because if you see your epoxide, the 3,4 position does not have oxygen functionality. So, basically what you need to do? You need to do a Barton deoxygenation, which you already studied, Barton McCombie deoxygenation, and then you remove this acetonide by H3O plus treatment. So, what you will get? You get this tetrol, Now, is absolutely simple. What you do? You first treat with tosyl chloride 2 equivalent to get the ditosylate, then you treat with sodium hydride, you basically get one of these epoxide, which is desired by you, this one. Now, in other case you can you basically have to invert it. So, what you need to do? You take it the pathway. So, you have this diol, okay. So, first you do a protection with TBS chloride 2 equivalent. So, primary group will be protected OH OTBS. Now, here you can do a inversion to follow the same way, otherwise you can do it other way also. You protect the secondary group at its methyl chloride. So, methyl chloride will basically give you OTBS at its methyl. Now, doing the methylation basically helps you the secondary group. Now, you are basically making it a leaving group. Now, TBS group deprotection can be done by TBAP. Now, TBAP is basically basic in nature. So, once it protect, it basically gives you O minus. Now, this O minus was there, and then you this O minus, this intermediate now intramolecularly react in SN2 fashion to give you a backside attack, to give you the epoxide of the other enantiomer. So, basically you have a divergence, mainly the way you basically do the entire synthesis. So, divergence is quite possible if you can follow the earlier pathway, that you carry the FGI and then do a stereo mutation at one step. Otherwise, here also you can basically do the same step, because these centers are inverted to give you the compound, to give you the epoxide. So, divergence is very much possible. So, chiral pull approach basically ends here, and next we will try to figure it out some other topics which will probably give you a little bit more emphasis. We will next focus on C2 symmetric molecules and strategic exploration of C2 symmetric molecule. We will just try to give you 1 or 2 examples, and then remaining lectures we will try to summarize how we came across through our entire course work. So, just go through the entire topic and particularly try to put more emphasis on the stereochemical strategies, which is seems to be very much important. So, have a good time. Till then, goodbye.